All right, section 1.1, we had left off last time on taking a look at some problem-solving strategies. We looked at the problem-solving process as well, but the problem-solving strategies is where we're sort of going to spend our time today. We're not going to be super specific, for instance, at writing down that we have done every one of the 4 parts of the problem. A lot of it we're going to check intuitively. We're going to ask ourselves questions in our head, on paper. We're not going to write a lot down, okay? So if you feel like, wait a minute, you told me there were 4 steps in this problem-solving process, we're going to do them. We're just not going to write all of them down, sort of like, step 1, I did this. Step 2, I did this. We're not going to do it that way, okay? So if you'll remember, these are the different problem-solving strategies that we talked about in brief last time. Looking for a pattern, examining related problems, examining a simpler or a special case, making tables and lists, identifying a sub-goal, making a diagram, using guess and check, working backwards and writing an equation. So we're going to look at a variety of these in our problems today. And this is where we left off on last time, talking briefly about this very interesting character named Gauss and how he was very unhelpful to his teacher, right? That's kind of where we left off. So Gauss's, just to remind you, Gauss's teacher had given them this assignment intending it to take them a long time to add up the numbers from 1 to 100, and Gauss answered very, very quickly. It did not take him very long, and he really did it using patterns. So what we're going to do is we're going to write down kind of a visual of what the numbers look like if we're writing them side by side and adding them together. So we've got 1 plus 2 plus 3 plus, and I'm going to put a dot, 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 and I'm going to write the last 3 numbers, which are 98, 99, and 100. Okay? They're all 1 apart. That's actually the pattern that's of value to us. That's important. They're all 1 apart. It's also important to realize that if you pair them up, nice things happen. So here's what I mean by that. What would happen if you added the first number and the last number together? What would you get? 101. What would happen if you added the second number and the second to last number up? You get 101. And that'll keep happening, right? Because you add 1 to the first number, you take 1 away from the last number as you're sort of working your way inward towards the middle. So what we're going to do is we're going to give this summation a name, and we're just going to call it S for the sake of doing our work, so we can reference it. And you'll see why this is a useful tool here in just a moment. So we're going to add this to itself is what we're really going to do. We're going to take these numbers and we're going to do this pairing of them up. And I used to not teach it like this, but once I saw somebody explain it this way, I really liked it. What we're going to do is we're going to add the same numbers in reverse order under the numbers we already had. So what we're really doing is a big old giant sum. We're adding S plus S. So when you add S plus S, what do you get? 2S. You get double what you had before. So why is it 2S? Well, because I've doubled everything, right? I'm adding it to itself. And as you guys noticed just a moment ago, when I do this, all of these individual sums that sort of go down like this, what are they? They're the same. What number? 101. They're all 101. So we're going to write in 101 for all of them. It's a lot of 101s. Now we could add 101 plus 101 plus 101, and that's easier than what we had before. I mean, that's easier than adding 1 plus 2 plus 3 plus 4 plus 5. I mean, that's actually an easier process, but there's got to be a better way than adding the same number to itself a bunch of times. Well, what is that? Multiplication, right? That's what multiplication is. It's repeatedly adding numbers together, right? So when we say 5 times 7, we mean 7 5 times or 5 7 times. I mean, that's what we mean. So we could use multiplication if we knew what? How many numbers we have. How many numbers do we have? 100. Because we started at 1 and we ended at 100, right? There are 100 numbers here. So we can actually do multiplication for this instead of doing addition. We can take 101 times 100. And that's easy Much easier than adding it to itself 100 times. So what is 101 times 100? Okay, I'm going to move this to the next slide so that I've got some more space. Just a sec. Okay, what was that, Hannah?
10,100.
Does everybody agree? Look good? Awesome. But that's double what I started with, right? Even if I didn't write 2s equals down, we should remember this is double what I started with. Why? We added it to itself. We added it twice, right? I mean, or we added it, which means we doubled it. We included all those numbers twice. So I need to take out sort of the doubles, you know, the fact that I doubled everything. So I need to take 10,100, I need to divide by and then divide by 2. So what would that give me? 5,050. And whether he showed it in exactly the way that we just did, this is the mental process that Gauss went through when he added these together. Pretty clever for a 6 or 7-year-old, don't you think? Yeah, definitely. So what we're going to do next is we're going to use this bit of information and we're going to try a similar problem. So we're going to find a sum of a bunch of numbers, but these numbers that we're finding the sum for don't start at 1. It's not exactly the situation I had before, right? But it's awfully similar. So what would you suggest that we do to start? What did we do last time? Add them to themselves, right? In reverse order is what we did, correct? So I'm going to give this the name S just because it's easier to keep track of everything. It'll make things lots cleaner. And I'm going to add these numbers to themselves in reverse order. So I have 147 plus 146 plus 145 plus, and then I have, let's see, so I have 37 and 36. So I've got 2s now on the left. What happens when I add each of these pairs of numbers up? What do I get? What's this sum? 183. Several of you are saying that. That's good. 183. Bunch of them. But the question then becomes, well, how many is a bunch? We can talk about a bunch of bananas, and that's not the same, right? So how many is a bunch? So how many numbers are there from 36 to 147? How could you figure it out? That might be a better question.
You just subtract 36 from 147.
So Amy's suggesting that we do this, I think. Is this what you said? You're really close. You're missing one tiny little detail.
That's just how many is between it.
You're getting really warm. You're still not quite there, but you're almost there. Let's imagine it like this. Okay, so imagine that you had all the numbers that started at 1. We don't now, but pretend it started with 1 and it went up to 147. How many numbers would you have? 147, right? But you don't have the first some numbers. How many numbers are you missing at the beginning? What do we not have? 35. There are 35 numbers at the beginning that we don't have. So we don't want to subtract 36, we want to subtract 35. The 35 numbers are the ones that are missing. 36 is where it starts. So we actually want to do the 147 minus the 35. So make sure and make that note to yourself that we are subtracting 35 because there are 35 missing, if you will, terms. How many does that give me? So 112 maybe?
Yeah,
Okay, that's what I thought. 112 of them. So we have 2s equals the 183, and it's times the 112. So what happens then when we multiply, what do we get when we multiply 183 times 112? Grab your calculator out if you have it with you, please. I don't even have this number written down, so somebody's going to have to help me.
20,496.
Fabulous. We're almost done. What's our last step in the problem? Divide by 2. So 20,000 will become 10,000 and some change. How much? 200 what?
48.
48. Look okay? All right. So I want to talk briefly about another variation that you will see at some point if it's, I don't know if it's group work or homework, but a variation of this that you will see is where it doesn't just go by ones, right? It sort of skips numbers, not haphazardly, I mean in a pattern, but like maybe it's every other number. It goes 2, 4, 6, 8, 10, 12, right? So let's just pretend like that's what we have now. We go from 2 to 20, but we only have the evens. Well, if we went from 1 to 20, we'd have all of them, and there'd be 20 numbers, right? So if we go to 2 to 20 and we only have the evens, how many numbers would we have? 10. We'd have half as many, right? Because we skipped every other number. Well, what if we skipped every third number? What would we have to do?
6 a little bit. Just be divided by 3.
We divide by 3 because we'd be skipping 2 terms. Every 3 terms we'd skip 2 of them, so we'd divide by 3. We'd only have 1/3 of the terms. Well, what if we counted by 5s? We'd be dividing by 5 because we'd only have every 5th term. Okay? So that's sort of the one difference that can happen in finding this number like the 112 is that the 112 works really well if you just have to take the first number minus 1 before the last number minus 1 before your first number, and you have every number in there. But if we only have the even numbers, we need to make sure we divide by 2 before we keep going. Or divide by 3 if we only have every third number. Yes?
Can we divide the 112 by 2 or by 3
You got
before
it.
we do everything else?
Yep, because that would be the number of terms you'd have. Yes. Okay, let's take a look at another problem. Examining a simpler case. This is one where I didn't want to spoil the fun and tell you the actual example last time when I sort of mentioned it, but this is a really good example of a simpler case kind of problem. We have a soccer league that has 10 teams, and each team plays each other team once. How many games will the league manager need to schedule at the start of the season? 9 per team. So is it 90? Not quite. Not quite, but you're close. So what we're going to do is we're going to simplify the process down a little bit, and we're going to consider just having 3 teams. Okay? So let's take a look at having 3 teams, and then we'll generalize what we did to the 9 teams or the 10 teams, whatever it was we said we had, and we'll see how that works. So let's say we had 3 teams. Let me write that down first, actually. And just for the sake of not having to write so very much, we're going to call them A, B, and C. Okay, team A, Team B, Team C. So I'd like for you guys to tell me, actually, you know what? You can do this on your own for just a second. I would like you to write down combinations of things of these 2 teams at once. So for instance, if A and B play each other, that's going to be A, B. I would like for you to write down all ways of combining the teams together. Okay, all of them. As many as you can think of to write down. And then check with the partner and see what they have and you have and see if you want to make any changes to your guesses. If you guess wrong, it's okay. We're going to fix it in a second anyway. So just give your guess at writing down all of the ones that you can think of. Once you think you're done, check with somebody nearby. I got this. How many did you get? These are what mine look like. What does yours look like? Okay, unless you forgot something, you got one of 2 possible answers. You either got 3 or you got 6. Who got 3? Okay, who has 6? Okay, so let me show you what happens. I'm going to write out all the 6 that you have first, and we'll talk about how the 6 end up giving us the answer, which actually should be the 3. Okay, so if we write down all the combinations, we would have AB and AC. We would have BA and BC. What am I missing? We would have CA and CB. These are all possible ways that I could write down the 3 teams in pairs of 2. But what you have to remember is the context of what's really happening. What's really happening is it's 2 teams playing a game against each other, right? So this game right here, AB, is the same as game BA. It's the same game. If I list all the combinations, I sort of am double counting that game, right? And I did it for every single game. So this one I'm going to eliminate because I already counted it. Here's my AC and my CA, so this one I'm going to eliminate because I already counted it. And then this one, BC and CB, are the same, and so this one I'm going to eliminate because I already counted it, and I end up with 3. Started with 6, ended up with 3. So let's talk about how we started with 3 teams and ended up with 6 first. How did we go from 3 teams to 6 potential games? What did we do? Think about numbers, what actually happened with the numbers. They doubled, right? Why? Why would I have 3 times 2 to get the number of games? What is happening there? 3 was the number of teams, right? That's my 3 teams. Why would it be times 2? Where would the 2 be coming from?
That's the 2 games that they're.
That's the 2 games each of them play. So what we really did when we do this is we really did 3 times 2. And we did another divided by something in a minute, but let me just do this times 2. This 3 was the number of teams, right? I had 3 teams. And the 2 was the number of games. What? Each of them played per team. It's the number they each played. Each individual team has 2 games. Why is it 2 games? Because there are 2 other teams, right? And then how did I get from 6 games, and then I marked some things out to get back to 3? What did I actually do?
Playing the same team twice.
Right. I eliminated the double counts, right? I counted everything twice. So I divided by 2 because I double counted everything. So let's again think about our actual soccer league. We have 10 teams. How many games will each team play?
It'd be 45.
Well, each team will play 9, right? Because there's 9 other teams. But if I use just 10 times 9, I've actually counted every single game on everybody's roster. But some of those games are the same game. And when I play you and you play me, that's one game. I've double counted things. So I end up having to divide by 2 to remove the double countings. So what is 10 times 9 divided by 2? Amy just told me. 45. So the league manager needs to know 45 games, right? He's got to get refs or umps, whatever it is he's playing for. I don't even know soccer that well. I have children who play. Is it refs? Okay. They have refs, apparently. So he needs to have refs. He needs to have field space. He needs to have, the timing to make that work. He needs to figure out how many weeks he's going to have, all that kind of stuff. He needs to know how many games in order to do that. Any questions on this one? All right. Oh, I like this one. We have a store and it sells bicycles and tricycles. There are a total of 15 cycles in the store, and there are 35 wheels on those cycles. How many type of each cycle are in the store? You probably saw word problems like this in like an algebra 2 class in high school, and you probably used equations to solve them. You set something up where you said something like x plus y equals 35, and then you did some other things like this, or x plus y equals 15. You did something with equations. And there's nothing wrong with that. But I mentioned last time that we're going to sort of steer away from the equations approach, because I know you've seen that before, but that's not what you're going to be teaching a child if they encountered this problem. And this problem can be done in a much simpler, more concrete way than equations. So I'm going to show you how to do that. And this is in my make a diagram category because this is probably not what you would have thought to do here. So I don't draw very well, so I'm going to show you what my cycle looks like. Okay? Here's my cycle. Hang on. I have bicycles and tricycles, right? That's a bicycle. That's my definition of a bicycle. Okay, looks just like that. Kind of looks like cherries, actually. But we're going to pretend that it's a bicycle. I'm supposed to have 15 cycles. So I'm going to draw this image 15 times. That's where I'm going to start. Okay, so you do too. Draw some kind of a bicycle image. You can be creative and draw well, or you can be not creative and draw not well, just like me. Okay, so this is actually 15 bicycles, right? I have 15 bicycles here. How many wheels do I have so far on all of these images? There are 30. How many am I supposed to have? 35. So I need to add some wheels. How many wheels do I need to add? 5 onto 5 what look right now like bicycles, right? Or they sort of look like bicycles. So I need to take 5 of these and I need to add a third wheel. And I think you should have the question answered, right? And how simple was it to draw the picture? I mean, like if I had 500 bicycles, this would not be a practical approach. I get it. But as long as the digits are small, this works really well. I've seen problems like this done with chickens and cows before. I've got chickens and cows on my farm. I've got so many feet. How many chickens do I have? How many cows do I have? Right? Stuff where you've got a physical image. Let's answer the question then. So how many bicycles do we have? I have 10 bikes. And how many trikes do I have? I have 5. Very good. Any questions on that one? All right, our next one is actually going to involve 3 problem-solving strategies because that's how cool we are now. We're going to use 3 in 1. Here's our problem. We have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be to have the greatest area enclosed for our chickens? So the strategy at the top says make a diagram, and we're going to make a diagram. What's written down on your paper apparently says guess and check, and we're going to guess and check. And we're also going to make a table because that's how cool we are. Okay, so let's start with our diagram. And you already saw my mad diagramming skills on the previous slide, and they just get better and better. So we're going to draw a barn, and because I feel like it, we're going to have a pink barn. That's my barn. By definition, I have told you this is a barn. Okie dokie? We have a barn. And along the side of our barn, we're supposed to have a fence. Now, when you fence alongside of a house, you never put the fence on the house itself. Think about every house and every building and every whatever that you know has a fence. The fence does not go along the side of the building. That'd be a waste of the fencing. So when you draw this, your fence is only going to have 3 sides. Make sense? Okay. Can you see okay? Or am I in your way, Jessica? Are you all right? Okay. All right. So we're going to draw a 3-sided fence along the side of our barn. So the green that I have on the screen is my fence. That is how far our diagram goes. Gives us a visual imagery. So let's take a look and think about our diagram for a moment. What can you tell me about this fence that I have drawn? What's important to realize? What shape is it? Let's start with that. It's a rectangle, right? I mean, like, people don't make circular fences. I mean, it's going to be a rectangle. Could even be a square, I mean, if it's a very specific kind of rectangle, right? But it's a rectangle kind of shape. What can you tell me about rectangles that's of value to this conversation? Okay, we've got an area thing, length times width is 0. We're going to use that. What else? Yeah, the top and the bottom in this picture are parallel, right? The sides are as well, but we really only have 2 green sides that are, that are in our discussion that are parallel. What else can you tell me about the two green sides that are parallel?
Should be the same.
They look shorter than the other one, and they're the same length. Those are both good features. They may not be shorter because it could just be I drew a bad picture, right? They look shorter right now, and they actually are going to be shorter in the end. But the fact that they're the same length is going to actually come about in our mathematics. So what we're going to do is we're going to actually give some letters to these, and I think Amy's the one who said something about the area being length times width. So since you mentioned those letters, that's the ones I'm going to use. Let's call this the W the width, and this one the length. We usually call W the shorter one. But it doesn't matter. If you labeled it differently, that'd be fine. If you want to use X and Y or S and T or Q or R, whatever, it doesn't matter. Okay, you can pick. All right, and so you had also mentioned that there's an important feature that area inside is length times width. We'll be using that. What else can you say about the fencing? I mean, they tell us something about how much we have, right? 48 feet. So what in this picture combined together makes 48 feet? Both W's and the L. So we also have, and it's not exactly the perimeter of the rectangle, but it is the fencing perimeter, right? So our perimeter, I'll call it P, which we know to be 48. Formula-wise, it's 2 times W, or W plus L. So I don't really even need the P equals, except to identify that that's what it is. This is an equation that we're going to be using. 48 equals 2W plus L. And now we're going to guess and check, but we need to do it in an organized way. And an organized way, certainly not the only one, but an organized way would be to make a list. So we're going to make a list over here. So you might be thinking, okay, what's going in my list? Well, lengths and widths. I mean, that's what I need, right? I need to choose lengths and widths that give me the area I need. So we have length, we have width, and we have area. Now, as I make choices for my length and my width, they have to satisfy this 2W plus L business. Okay? So I can't just pick like any width and any length I want. I only get to pick one thing. So somebody give me a pick for, I listed L first, so somebody give me a pick for L. What would you like L to be? 12. Okay, so we're going to try 12. Did you say what? I'm
I said
sorry.
24.
24. I'm sorry. 24. If L is 24, how much do we have left over of the fencing? 24. And I have to split that between the two W pieces, right? So how much will each W be? 12. And then how do I find my area? Well, I multiply 24 times 12. What does that give me? What is it? 288. And it's square feet, so I'll write in feet squared right here like this for now. All right, I need a different value now for L. Or a different value for W and then determine L. I don't care which one you want to pick. So do you want to pick another W or another L? Ooh, don't everybody answer all at once.
36.
36 for the L?
Yeah.
Okay. 36. So I have 36. How much is left over? 12. And I have to split it evenly, so that gives me 6. So then my area would be 36 times 6, which is what? I don't have that one written down, so 216?
Yes.
Okay. That's less, right? Less than we had. We want it to be more, I mean, or at least we want it to be as big as we possibly can. Our goal is to have a maximum amount of area. So what do we do next? Well, we look at the numbers and we say, well, that didn't do it. So maybe we pick something closer to 24. I mean, 24 had a bigger area, so something closer to 24. So somebody give me another number closer to 24 than 36 is. 20, okay. So if I used up 20 in the length, what would the width be? 14? Is that right? I think so. And then what is 20 times 14? Oh, well, that's closer to the first one, right? Was it 280? Yeah. Still not bigger, but it's closer. So maybe we still need to get closer to 24. I mean, like getting closer made it closer, so maybe we do 22. So 22, what would that leave me for my width? So what is 22 times 13? I think it's 286. Is that true? Okay. Still not as big as the 24. Okay, so we've kind of exhausted, if you will, the numbers that are slight. Let's look at the W values for the moment. If we're comparing it to the 12, the 13 and the 14 are the numbers just a little bit bigger than 12, right? So let's try numbers just a little bit smaller than 12 because it's looking like our first choice right now anyway is the best choice. So let's try a number a little bit smaller than 12. So maybe 10, or maybe you want to pick 9 or 11. What do you want to pick? You want to do 10? So if the width is 10, how much do I have left for my length? What would I have left? 28. Okay, good. And then I would have 28 times 10, which gives me 280. Hey, I saw 280 once before, didn't I? Okay, we're going to try one more thing. We're going to try this 11 down here because it's the only other possibility that sort of hasn't been checked out that's really close to the 12. So if I have 11, what will I have for my length? 26. And what do I get if I multiply 26 times 11? 286 is right. So we're guessing things in an organized way, trying to make sure that what we picked, and we actually had the right answer at the beginning. So well done on choosing a great answer to start with. This one would be the one that we want. We need to make sure we answer the question that was asked. It says, what lengths would the sides need to be to have the greatest area enclosed for our chickens? So the lengths of the sides is what it's asking for. So what are the lengths of my sides? 24 feet? $12 feet and 12 feet. Seems like everybody's raising chickens these days. So, any questions on this one? Okay. This is one of the fun ones. I like this one a lot, working backwards. One winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What was the temperature at midnight? Okay, so we are going to work our way backwards. The first thing we're going to do is we're going to write down forward what we have. And I think probably the best place to start is to write down the times of day we keep talking about in order. So what is the first time of day that we are referenced in this problem?
Midnight to 5 a.m.
Yeah, it's midnight. And the second one is 5 a.m. What's the next one? 9 a.m. And I think there's one more. Noon. Okay, so what happens between midnight and 5 a.m.?
12:15.
Fell 15 degrees. What happens between 5 a.m. and 9 a.m.? The temperature doubles. At least the number of it, that's associated with it doubles. And then what happens between 9 a.m. and noon? It rises or increases, right? Another 10 degrees. Did I write that down right? Looks okay. And there's one more piece of information I haven't written down yet. What is it?
It's 32 degrees, I think.
Yeah, we need to find out these temperatures. And I know that the last temperature is 32 degrees. So we're going to go backwards. If it rises 10 degrees to end up at 32 degrees, what was it before it did that? 22 degrees. If it doubled to end at 22 degrees, what was it before that? 11 degrees. And if it fell by 15 degrees to get to 11 degrees, what temperature was it before that? 26 degrees. And that is our answer. 26 degrees at midnight. Any questions on that one? All right, one more tiny little thing before we stop. This is going to come up in your homework problem set or your group work problem set. I can't remember which one. It talks about the 12 days of Christmas, and so we need to remember which ones they are and what order. But this is also a really cool place where I can show you there is actually religious symbolism in that 12 days of Christmas, which I find to be pretty interesting. So the 12 days of Christmas. Do you remember what the first day of Christmas is? Partridge in a Pear Tree. So the partridge in a pear tree, I think that's the only one I don't have written down here, is the partridge in a pear tree. The first day of Christmas, that partridge is true love, God. The second one, the two turtle doves, is the Old and the New Testament. 3 French hens is faith, hope, and love. The 4 calling birds is the 4 Gospels. The 5 golden rings is the Pentateuch, which is the first 5 books of the Old Testament. The 6 geese a-laying is the 6 days of creation. 7 swans a-swimming is the 7 gifts of the Holy Spirit. The 8 maids a-milking is the 8 Beatitudes. 9 ladies dancing is the 9 fruits of the Holy Spirit. 10 lords a-leaping is the 10 commandments. The 11 pipers piping is the 11 faithful apostles. And then the 12 drummers drumming is the 12 points and doctrine in the Apostles' Creed. So you're going to need this list. You're going to need the left-hand side of the list for your homework, but I wanted to show you the right-hand side of the list because I think it's pretty cool. All right, so we're going to take a look at group work now.